Hello, welcome. We're going to first start with some discussion and examples for lesson 3.3. So I'm going to share my screen with you all. So you can see in the book, if you're on page 189, that's where, well, the bottom of page 188, it starts with the two basic rules of probability. We kind of introduced them in class on Tuesday. The first rule is the multiplication rule. And we talked about in class right here, if this part where it says if A and B are independent, then the probability of A given B is equal to the probability of A. What I really spoke of was that if they're independent, we can then use this rule. The probability of A and B is their individual probabilities multiplied together. Now we are going to use the thinking, a little bit of the thinking here of this rule. The probability of A given B, it's equal to the probability of A and B divided by the probability of B. We're going to use that thinking, but I'm not going to be assessing you over that in the problems that I'm giving you. We're also going to be using the addition rule. So the addition rule is the or. If you hear if A and B are defined in a sample space, then we're looking at the or situation. The probability of A or B is the probability of A plus the probability of B minus the probability of A and B. And we talked in class about the probability of A and B being that overlap, if you can be in both A and B at the same time. So if they are mutually exclusive, then this is going to be 0. You won't have to worry about it. And that's what they show right down in this second line. But I think it's best if we do some examples so you can see. So I'll let you read through examples, but I'm going to work on the try-its. So try-it 3.15 says, Helen plays basketball. For free throws, she makes the shot 75% of the time. Helen must now attempt 2 free throws. C is the event that Helen makes the first shot. P of C is 0.75. D is the event that Helen makes the second shot. And the probability of D is also 0.75. The probability that Helen makes the second free throw, given that she made the first free throw, is 0.85. What is the probability that Helen makes both free throws? So let's look at this on my paper here. So they gave us, this is 3.15, try it. So it says the probability that Helen makes the second free throw, so probability of D, given that she made the first free throw, is equal to 0.85. What is the probability that Helen makes both? So what is the probability of D and C? Okay. So if we go back to our formula from the prior page on the multiplication rule, this would be equal to the probability of, the probability of D and C is equal to the probability of D given C times the probability of C. Okay, so we know the probability of D given C is 0.85, and we know the probability of C is 0.75. So we can multiply them to find the probability of D and C, making both shots. 0.85 times 0.75, and that probability is 0.6375. So let's look at try it 3.16. 3.16, I'm going to read it along with you. It says, a school has 200 seniors, of whom 140 will be going to college next year. 40 will be going directly to work. The remainder are taking a gap year. 50 of the seniors going to college play sports. 30 of the seniors going directly to work play sports. 5 of the seniors taking a gap year play sports. What is the probability that a senior is taking a gap year? So even though it's not covered until the next section, we've already done one of these two-way tables, these contingency tables that's here in 3.4, where we have one variable going vertically and one going horizontally, actually one going vertically here and one going horizontally. So for this situation, I'm going to build one of those for the 3.16. Did you get it? Or try it here. Because we have two questions. One is they're going to college, they're going to work, or they're taking a gap year. Okay. And then the other question is if they play sports. So okay, and then we're going to have totals. So I'm going to show you how I drew this, because their question is, what is the probability that a senior is taking a gap year? Okay. Now, in this question, because the question is only referring to the seniors taking a gap year, we just need to find out how many of them are taking a gap year. So there are 200 seniors in all. So let's go, I'm going to take you to my paper here. I started thinking about this like making a table, but I know that 200 in all were surveyed, or there were 200 students at the school that were seniors. 140 of them are going to college. 40 of them are going directly to work. And it says the remainder are taking a gap year. So that means 200 minus 140 minus 40 is going to equal the gap seniors. So that means that there are 20 taking a gap year. And it says find the probability that a senior takes a gap year. So the probability of taking a gap year is just 20 out of the 200 seniors, which is 1/10 or 10%. So in this case, we didn't really need to make a two-way table because it was only asking a question about one of the variables. So let's go to it's really not that like they have to worry about. Let's go to try it 3.19. And that is on page 193. So try it 3.19, sorry. It says a student goes to the library, but events B equal the student checks out a book, and D is the student checks out a DVD. Suppose that the probability of B is equal to 0.4 and the probability of D, the DVD, is equal to 0.3. The probability of D given B is equal to 0.5. So let's look at the some of these on our on my paper here. Okay, so question A says find the probability of the complement of B. So that means that's 1 minus the probability of B. We talked about the complement in class on Tuesday. And so that's 1 minus 0.4, which would be 0.6. Then B says, find the probability of D and B. If we assume independence, so we're assuming that getting, if they're checking out a book or checking out a DVD are independent of one another, then we can multiply their individual probabilities together, which would be 0.4 times 0.3. Which is 0.12. I'm skipping question C. And then D is the probability of D and the complement of B. And so that is going to be independent again. So that's going to be 0.4. Oh, sorry. D, which is 0.3 times the complement of B, which is 0.6. And that comes out to be 0.18. I also wanted to look at a couple of good examples in the problem section. So question 80 in your book. So if you go to problem set, here we go, on page 222. It says on February 28th, 2013, a field poll survey reported that 61% of California registered voters approved of allowing two people of the same gender to marry and have regular marriage laws applied to them. Among 18 to 39-year-olds, the approval rating was 78%. 6 in 10 California registered voters said that the upcoming Supreme Court's ruling about the constitutionality of California's Proposition 8 was either very or somewhat important to them. Out of those California registered voters who support same-sex marriage, 75% say the ruling is important to them. So C is the California's voters that support same-sex marriage. B is California voters who say that the ruling is important to them. And A is California registered voters who are 18 to 39 years old. Okay, so A says, find the probability of C, which is the probability of California registered voters who support same-sex marriage. And they told us that 61% of California registered voters approve. So that would be 0.61. Find the probability of B, California registered voters who support or who say that Proposition 8 is important to them. And they told us that 6 in 10 California registered voters say it's important to them. So that would be 6 out of 10 or 0.6, 60%. Then C says, find the probability of C given A. So the probability that, given that they are 18 to 39 years old, what is the probability that they are supporting same-sex marriage? They gave us this as well. It says right here, among 18 to 39-year-olds, the approval rating was 78%. So that is the probability of C given A, which is 0.78. Okay, we're going to skip D and E and F because I really don't want to focus on those contingency probabilities. Let's look at G, the probability of C and B. Oh shoot, I need those. Turn it. In this case, we do need those. Well, that gives us practice on the first couple, kind of reading those. Let me show you my paper here for just a moment, so you can see how I wrote those first couple that we did. The probability that they were California voters that supported same-sex marriage, and probability B was the probability of voters that it was important to them, Proposition 8 ruling, and then C was the probability that given that they were in the 18 to 39-year-old age group, what is the probability that they actually supported? So that age group seems to be a higher percentage of that group support same-sex marriage. Okay. I also wanted to look at number 82. I thought this would be a good one because we haven't done as much with card games. So this is a roulette board of where you can place your bets on the roulette board. And I'm going to give you a copy of this for the test if I were to ask any questions, don't worry. So you can bet on red or black. You can bet on even or odd. You can bet on individual numbers. And you can see on this particular board, there's an American and then there's also a European. I can't remember which one this is. But there's 36 outcomes plus 0 and double 0. So there's not just red and black. It could land on a white. So there's actually 38 outcomes if they're individual outcomes. You can bet on the first dozen, which would be 1 through 12. You could bet on the second dozen, which would be 13 through 24. And you can see they line up here, 13 through 24. You can bet on the corners. There's so many different bets. So let's just look at some of these here in question 82. It says, list the sample space of the 38 possible outcomes in roulette. So I'm going to show you my paper so you can see how I'm writing these out. So the sample space for roulette, and they did say this was, they didn't tell us it was American or the European, but for this one, because there's so many, you could say 1-38 and then make comma 0 and then comma double 0. Make sure it's in brackets for the sample space. You bet on red. Find the probability of getting a red. So the probability of red is, there's 38 possibilities and there are 18 red. 18 are red. So let's just write this out. 18 are red, 18 are black, and then 2 are the white, the 0 and the double 0. So it's not quite 1/2. So that's where they get you. It's 0.4737. So about 47.37%. Then letter C says you bet on the first 12, which is the first dozen. So find the probability of the first 12. Well, the first 12 is there's 12 items that you could land on that would win in that bet out of 38. So 12 divided by 38 is 0.3158. D says you bet on an even number. What is the probability of an even number? So the probability of an even. So on the evens, there are 18 evens, just like there's 18 reds. So that's going to be the same as the probability of red, which is 0.4737. E says, is getting an odd number the complement of getting an even number? So the complement would be just the opposite, right? 1 minus that, but that's a no, because you could also land on 0 or double 0. So it's not a complement. A complement would be everything other than the even. And then letter F says find 2 mutually exclusive events. So 2 events that can't happen at the same time. So the probability of the first dozen and the probability of the third dozen. Because I can't land in the first dozen, like the number 7, and then still be in the third dozen. They're mutually exclusive. And then G, are the events even and first dozen independent? So if I get an even, does that change my possibility of getting in the first dozen? And so let's look at our book here so you can see that, because it says, are the events even and first dozen independent? If I get an even, so if I get 2, 4, 6, does it change my possibility of getting in the first dozen? Yes, it does, because if I get an even, I might not necessarily get in the first dozen, right? Because there's lots of evens that are down here. So they're definitely dependent. So they're not independent, is what we're going to say. So catch me back for 3.4. We're going to tie more of this in, talking about the contingency tables. And then 3.5, we're going to talk about tree diagrams, but we're still going to be tying all these other concepts in as well.